You know what I mean by conditional property? Something like this. From example 68, that kind of thing.
Then it's like
And and once you're done with that, I want you to do an example, like example 67. I'll tell you what. Example 67, I want you to do something pretty close to this, but don't make the coin fair. Make the coin biased, but still be counting heads. And and I want you to do two things. What should the correct structure of the probability be so that your biased coin situation has a probability that sums to one? All right. So this is a simple case where the coin is fair, but I want you to do the case where the coin is unfair. But give me the valid normalizing factor. So when I say unfair coin, you're going to alter the probability of it. So you're going to need to know what should be the what should you what should you write this to be so that it's a valid probability distribution? Then answer this question. I want you to practice geometric progression sums. What's the probability of getting what's the probability that you have to toss at least at least four times before the first head appears? That's my prompt ask you to do. Everyone does the same problem, but with an unfair point. You choose your unfair point. I want to know what's the probability of you having to toss at least four times before you saw your head. Right? This should give you some practice in geometric progression. Now, if you have any doubts or don't understand what I just said, please raise your hand. I'll come and help you. Right? I want you to redo this problem with an unfair coin, but still measure the same thing. How many tosses do you need to do until you see your first head? And I want you to, for your coin, produce the correct probability statement. This is in general for n. This is, I need to see n tosses before I saw my first head. But this is for a fair coin. I want you to do it for an unfair coin. Then answer the question, what's the probability that I had to toss at least four times before I saw my first head? All right? See if you can do that. There are two ways to do that problem. I want you to do it the geometric progression way, right? The geometric series way. Any clarification need to let me know, all right? If you don't understand what I asked you to do.
yeah, that's just okay. So it has to be actually. Yeah, so actually the last time I did any. No, actually, this was probably, well, actually, this. Base here and all just
Yes.
So kind of concerned about
Okay. So
like
okay. So
The first,
yes.
off the unfair.
So X.
yeah,
We were X.
yeah.
Okay. So find the property of X. Then this is defined as n. Which okay, which means what? So in this context, more than 5 elements, it says only 1, 2, 7. So this is
Okay.
Why does it? That's good.
Okay.
That's it. What part of it's making you?
They were confused to why it wasn't just 0.6.
Oh, because that's a good question. Because 0.07 is an intersection event, but I want the conditional intersection over the event.
This one,
Yeah.
sure. Is it defined or do we know that it's 0.6?
Conditional property is not the same. And over the probability of the right side condition with events probability.
Thank you.
Yeah,
Thank you so much.
of course.
Okay, so what do we want?
Just make like something to like 1/3, 2/3.
Yeah.
Okay, yes.
Yeah.
So yeah, 1/3.
So,
So now we have to replace it with number.
So that comes from that
Oh,
from the intersection. Like you have this, right? You can divide both sides by n. But this divide by n. It's just here. But just divide that. Just
Very good. That's exactly what.
That's just like divide this side by probability. Probability. If it's like if you are to be given its
This is like the one.
And those are low joke. That's why I'm like forcing you.
Yeah, it's like, oh, you restrict yourself there. It's just like finding the exact ratio.
I'm like what I'm trying to get the class to be very comfortable with is geometric series pop up all over the place, so you must be very comfortable with what's the first term, what's the common ratio, and then you're able to get it. I mean, in this case, you can do the problem using a complementary event, but I want you to use the infinite geometric series. Yes.
So you said we had to make a modification.
Yes, change it to an unfair point.
Yeah.
How unfair is up to you.
Okay. That's all of that.
And, but answer the same question. What's the probability that I have to toss 4 times or more before I see my first hit?
Well, this is ours. A is so this is this is essential.
So get the probability distribution
You
first,
have,
right? Get that first.
The way you generalize the PR, like a function I have set. It's just you right now. That's actually.
Right, and then once.
This was not. Go on for the extension.
At least 4 times. So basically, you would case 4, 5, and that's why I'm trying to get across. You all know the infinite series A over 1 minus R, right? Oh, so the infinite geometric series sum, first term A over 1 minus common ratio. So you need to identify the first term and the common ratio. What are you trying to sum? So don't worry about this. You can hand it in to me after class. We'll go on to something else for now. And you can always leave it outside my door. All right? Okay, let's look at some other example. We are going to skip some examples. Now, the reason for the skip is because this class uh, has questions which I actually use for preparing students for the P exam, if you want to know. So they are a little bit higher level, and I don't require them for this class. So you can just put a cross on the example. But I put them all together so I don't go crazy with it. Here are examples for this class. Here are examples for another class. So there are examples which are not covered in this class. 69 is one of them. So you can cross that out. All right. So we will skip 69. And then we'll just go to, we'll skip 69 and then go on with our slides okay, yes. Okay. So we'll skip 69. Okay. So we have introduced, actually, in a way, I've tried to introduce these things in a, I don't know, as a more subtle way. I was actually introducing what's called the probability mass function for a random variable. A probability mass function is that statement of probability assignment values. It can be, okay, so a probability mass function tells you the probabilities for each of the values of the random variable. It can be given as a table, like example 66. It can also be given as a formula, like example 67. But anything that describes the probability of each value of the random variable in the range is called a probability mass function. Now, the term PMF, probability mass function, is used when the random variable is discrete. Later, when we use a continuous random variable, it will be that there's an equivalent concept, not the same thing, called a probability density function. That's PDF. That's coming up. For today and for a while, we are only going to be dealing with discrete random variables first. So a probability assignment for the values of the random variable is called a probability mass function. Because you know what? It assigns mass, weight, to each random variable according to, it's like a weighted average kind of thing. All right. So the only rule that you have are two. Of course, every probability that you assign must not be less than 0 or more than 1. And the sum over all the values that it can take. Now, of course, this is, of course, a finite range. If it's infinite, then it just means that when I sum all the assigned probabilities from 1 to infinity or whatever, for all the values in it, could be infinite. It must sum to 1. And so when I ask you to generate that example for the ICT, you will find that in both cases, the problem that you have done, the total probability will sum to 1. If not, something's wrong with your probability assignment. It has to sum to 1. It's easier to check that for a finite range, of course. But for infinite range, you might have to resort to using a GP or things like that. And you know, sometimes if you have a very evil example that doesn't have a GP relationship, it could be more challenging to find the sum. And that's where all those esoteric sums, you know, people have been all through the hundreds of years, people are wondering, what's the sum of this infinite series? What's the sum of this infinite series? And people came up with ingenious ways to come up with those sums. The geometric series is just the most basic one. There are all kinds of nice problems, right? You all know the famous harmonic series and summation. Not harmonic, that's the wrong word. I'm talking about the sigma 1 over n squared, for example, that kind of thing. That could be a probability mass function because if you scale it accordingly, it does sum to 1. Okay? I don't know whether it amazes you that people made such strides in math centuries ago. It's amazing, honestly. Yes, education is more democratized now. There's far more people having access to that. Maybe that's why knowledge is exploding because there's just more people learning stuff. Learning used to be restricted to a very small class of people. So there were just, I think, less things discovered. Now there are more people accessing these things, and so the probability that you come up with something is going to be higher. So it could also be due to the fact that there was no TikTok last time. So people just spend their time more wisely. I think there's a lot of brain rot as well. So anyway, so you know, I mean, people used to write letters, you know, challenging each other with math problems. Now what do? We text nonsense to each other and send cat pictures and all that. People used to write letters saying, I hereby send you this math problem. And then they would feel, oh, it's actually a kind of a wanting to, what's the word that we use now? Flex, right? People want to flex to their mathematician friends. Say, see, I know how to solve this, you don't know how to do that. You know, human nature is the same, but the manifestation of it is different, right? Sometimes. Okay. Anyway, so sometimes people shorten this thing. Are you confused by this notation? Capital X, little x. Okay, let me explain. I've not talked about this yet. Capital X stands for the random variable, but little x stands for the values it could take. All right, so that's why we differentiate between them. This is the random variable, the number of tosses of coin. But you know that the number of tosses before you see a head could be 1, 2, 3, 4. So the little x stands for the values the random variable can take. Capital X, uppercase X is the random variable itself. Okay, so let's look at example 70.
and talk about this one. Okay, so I said we're skipping 69, 17. And again, this is just some revision of your combinatorial things that we learned before. A committee of 4 is to be selected from a group consisting of 5 men and 5 women. Let X be the random variable, see, that represents the number of women on the committee. Can you create the probability mass distribution? So this is some practice for you. Let's think about the problem. What does X measure? X is the variable that represents how many women are in the committee. Now, how big is the committee? See, the committee is of size 4. So ask yourself first, always establish the range first. What values can X take? Anyone? Yes.
0, 1, 2, 3.
That's right. 0, 1, 2, 3, or 4. So build a table like that. X could be little x, right? Little x can be 0, 1, 2, 3, or 4. And now it's just become a problem. Okay, what is the probability of X being 0? Where X is how many women ended up on the committee? What is the probability that the committee has no women? So this is just an NCR problem all over again, right? It's NCR because we are not concerned with the order in which you select people. It's just who gets on the committee. That's it. Okay. So give it a think before. This is not a difficult problem. Just give it a think, and I'll show you the answer. It's a whole bunch of NCR things. And of course, when you generate the probability mass distribution or mass function, make sure it adds to 1. That's all. It's embarrassing if it doesn't. So make sure it adds to 1, right? It has to add to 1 so that it's a valid probability mass function, all right? I'll give you a minute or so. At least do 1 or 2 cases. Make sure you understand how to do at least 1 or 2 of these cases. Okay, do you agree with this? In general, if I'm trying to do it all in one step, I could have, as Anya pointed out, you can have 0 women, 1, 2, 3, or 4. If you cannot see this immediately, then do it case by case. Let's test and see, is this formula correct? What is the probability that there is 1 woman on the committee? Well, to choose 1 woman, don't you have 5 women to choose from? So 5 choose 1. Don't you have 5 men to choose from? Yes. And don't you have to choose another 3 men? So 5 choose 3. Like that. So doing this is just saves you a bit of time, but you can do it separately if you wanted to. So case by case. So the case for 1 is quite obvious. 0 is maybe easier. If I want 0 women in the committee, it just means 5 women choose none of them. 5 men choose 4 of them. And in total, there are 10 C4 ways to form committees. Is this okay? So you can finish this on your own, all right? It's not, anyway, then you can compute these numbers and it will sum to 1. So of course, if you are doing this, if it's a homework problem, I would say check your answer by doing it 2 ways. Compute them 1 by 1. But if you are confident that your argument is correct, you always can leave out 1 case. Maybe leave out the most complicated case and do 1 minus the other. You know it has to add up to 1. Okay? But you can always check your answer from another direction if you like. Okay, the next example is, okay, so we're going to talk about CDFs now. Okay, so this is a very important and possibly new concept. So I'll ask you to Anyway, this class always pays attention to me. It's very I mean, as a professor, I teach intro stat and I also teach this class. The two couldn't be more different, honestly. Intro stat classes are a totally different animal. Like the 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 amount of number phobia is the fact that in this class means you don't have number phobia. Okay. Anyway, so what's a CDF? Well, technically, a CDF answers this question. A CDF answers, tell me what is the cumulative probability up to and including a certain value of your choice. That's what a CDF is. It's a cumulative probability function. It accumulates probability. What is the probability of you seeing something like this or less? And you need to answer this question for all real numbers. If you can find this function, you have basically found the CDF, the cumulative distribution function. CDFs are very important for a bunch of reasons, but for now, we'll just show you how to find them, all right? So how do you do this for discrete random variables? Now, of course, for continuous, you have to integrate all in good time, not yet. For discrete random variables, you add, you just add. So if I want to know the probability that x, which is discrete, is a or less, well, sum of the probabilities until that point. Okay, so let's do an example, all right? So example 71, consider the following probability mass distribution. So this is not a CDF. This is just a PMF or PMD, okay? This is a distribution of probabilities for a discrete random variable. It can take values 1, 2, 3, or 4, and with these probabilities. Find a formula for, okay, notice capital F. This capital Fx just means what's the probability of you seeing this value or less, right? So let's take it slowly. The CDF follows this rule. Now you can copy this down first. Then I'll ask you, do you agree with this? Why is this a CDF? And do you even agree with this answer? Okay. Didn't we say, first of all, that a CDF must be defined for all real numbers? Look at the ranges of things you could ask. Have I covered everything? I actually have. And a CDF has to be defined for any real number on the whole line. That's not as difficult a concept as you might think, because, see, this value of x never gets anything less than 1. So if I choose to ask you this question, what is the probability of me being less than, half? Half is less than 1. There's no probability like that, so 0. But at 1, something happens. If I ask you specifically, what is the probability that x is less than or equal to 1, it translates to basically saying x is 1. And so that's why it's 0.25. But think about it logically. Is it correct that the probability that x is less than, less than or equal to 1.5, isn't that still 0.25? Because can x take any value between 1 and 2? No, it cannot. Yet, a CDF needs to be defined for every possible value that's real. So you have these ranges that you set up, which are informed by the mass function itself. Why are these endpoints chosen 1, 2, 3? These are chosen because of this thing. In other words, if I had changed the 3 to a 30 and this to a 400, what would happen? If I change this to 30, do you see that this will become 2 less than x less than? 30. See? So these are dictated by this. Because you basically need to document what happens to the probability that you accumulate as you shift through all possible real numbers. Okay, so take some time to digest this. This is a definition of a CDF. It's not hard to generate, but it can be a little bit of an abstract concept, especially this part. It needs to be defined for every real number, not just numbers in the range. So there's a lot of places where it seems like you're asking a silly question because what's the probability that x is less than 2.73? That's a valid question. Less than or equal to 2.73 means you're somewhere between these two. And so your accumulated probability is only 0.7. But you have fulfilled the criteria. A CDF has to be defined for all the numbers. Now, if I wonder why is definition like that, there are some high-level math reasons. Okay, but we will leave that there. So that's the definition of CDF. Now, I want to ask you, can you draw this function? Give it a try, right? Before I show you the answer. Or can you describe what this would look like if you drew this function? Yes. Oh, sorry. Does anyone know what this looks like? Just describe it actually. If you plotted or sketched this, what would you see? Yeah, anyone know the answer? You can describe it to me. What do you see as the what? Yes. This will be the step function kind of thing, all right? So you see like steps. So you should see that this translates to a plot that looks like this. Something like that. Now I'll explain, all right? This picture should be improved. This red line extends actually all the way to negative infinity. So please do that in your picture, all right? It goes on actually. Why are there holes here? Because at 1, something exciting happens. At 1, the probability jumps to the accumulated probability jumps to 0.25. But there's none before 1. So if you want, you can put a solid circle here. A hole has to be filled up. So this is empty, but here's solid. This is empty, this is solid. This is empty, this is solid. Why is this important? And also, this graph goes on forever. Drag it on. Why is this graph important? Actually, do you realize that every discrete random variable, let me say it more carefully, every discrete random variable will have a CDF that looks like stairs. So, care to infer, can I ask a question? What do you think the continuous random variable CDF is going to look like? If you're a continuous random variable, just a shot in the dark. What do you think? Yes. Yes, it will be continuous. That's right. Discrete random variables have CDFs that look like staircase. And it's very interesting that you can only have countably many to be a discrete variable. You cannot have uncountably many steps. Mind you, you can have infinite steps, but countably infinite. But if you don't like these things, don't worry. I'm not going to. These things just interest me greatly, right? You can have infinite steps, but it's countable. Yeah. Anyway, that's what the CDF looks like graphically. All right, let's look at another example. Okay, see, now I'm saying this is the reverse. I'm giving you now the CDF of a random variable. First, tell me, is this a staircase? If you plotted this, you get a stair function. You still do, which means x is what kind of random variable? It has to be a discrete. So what I'm saying is, can you reverse engineer and give me the mass function? Can you try to work that out? So in other words, give me back the mass function. So CDFs are actually very fundamental. Some people argue that they are more fundamental than the mass function. From the CDF, you can get the mass function, you get it back. And you can recover it. What is the mass function based on this? See if you can write it out, right? It's not a very difficult question. See if you can write it out. what are the values? What is the range of values, first of all, that makes sense? And what are the probabilities assigned to each? So can anyone tell me what is the first smallest value that x can be in the range? Can x be 0 with some positive probability? Yes, 0. So 0 is one of the things x could be that has positive probability, right? So you will find that px is 0 is this. The probability that x is 1 itself is, of course, 1 or less minus the probability of u being 0 and so on. That's how you reverse engineer the mass function, right, from a CDF. And notice what I'm doing. Be smart about it. You can always do it as 3 versus less than 3. Okay. But one thing I want to point out is in all this discussion of CDFs, don't forget the definition of a CDF. I'll flash back to this slide, don't worry. A CDF is defined as x less than or equal to a number. You have to include the value. I mean, could you define CDF this way? Yes, but people don't like that because this ends up with a lot of open intervals and all that, which can be a little bit dicey to deal with. So that's why the definition closes it. Closes into it. Include the endpoint, right? For the definition of a CDF, you include the point of interest. All right. Okay, and that's it. That's how you go backwards from a CDF back to the PMF. Okay, a few other examples. Can you try to do this? A pair of fair dice is tossed, and X is the sum of the dots on the faces. Find the CDF of X. Again, you don't have to do the whole question, just do a few, all right? All right, six-sided, okay, six-sided dice, fair. X is the sum of the dots on the two faces that you get. Find the CDF of X. Now, obviously, start with the PMF. It's easier that way. When you toss two fair dice, what's the smallest sum you could get? 2, right? So the range of X starts from 2. It cannot be less than 2. What's the probability of that? Okay, you can work that out. Then what's the next thing? Can you get a score of 3? Yes, you can. What's the probability of that? All right. So slowly work out the probabilities and you can get a CDF. So again, I think this is not a very difficult problem. So first, work out the range that X could be. And then after you have the range of X values, slowly compute the probabilities. So I hope you can see that the probability that you get a score of 2 total is this, right? Because you must get 1, 1, which happens with probability 1, 6 times 1, 6. You know from independence, you can multiply. A score of 3, you have to be a bit careful. A score of 3 happens when you get 1, 2, or 2. There's 2 cases. And so on. So you just make sure that your probabilities add to 1. And then making a CDF is, as usual, something like this. Just remember that your CDF has to cover every possible gap. Every value in the real line has to be there. So less than 2, there can be no probability accumulated, and anything from 2 to less than 3. It's pretty basic. So I hope you all are not confused about why these can have less than. That's not the CDF. This is just a range. The CDF definition has to include the value that you are considering. That's the definition of the CDF. These ranges are anything you want it to be, as long as you cover the whole line. Right? Okay, let's see some other example. Oh, this is a nice one. Okay, so here are claims and the probabilities, okay? A lot of the examples are insurance-based for obvious reasons. So there's an 80% chance that no one claims anything. And so on, right? So here's your probability distribution. How much should the company charge as its average premium to break even on costs for claims? All right. So before we do that, we are going to discuss what is the expected value of a random variable. Okay. The expected value is a very intuitive formula. Sometimes the expected value is called the mean, just so you know. So expected values, right? They are defined this way for a discrete random variable. You take the probability of that random variable taking a particular value, scale it by that thing. Now, this is exactly really the same algorithm you use to calculate your GPA. Okay, now I'll tell you what. When Hope had not just 3 credit classes, most Hope classes are 3 credits. That's not true for all, but far more courses are now 3 credit. But back in the bad old days, or some students like the old system, where you had 2 credit classes, 1 credit class, 4 credit class. You know how you got a GPA? You take, okay, let's say you got an A in a 4 credit class, and A is worth 4 points, and you multiply that by 4 because 4 points and it's a 4 credit class. But let's say another class was a 3 credit class and you got an A minus. Now A minus is worth 3.7. So you take 3.7 and you multiply by 3. You weight it by 3 because the credit hours. That's exactly what's going on here. You take all the values that a random variable can take, scale it or weight it by the probability. Does it make sense that this gives you an expected value? Is it reasonable? You scale every value that you can take by the probability, which means things that are higher in probability will rank higher and contribute to your expected value, which makes sense. Okay, you would expect that, this is for expected value. You would expect the random variable to be hanging around a number that has higher probability. And that's why you scale by the probability. So the definition of expected value is very intuitive. Now let's look at this example. All right. So the claim amounts are given there. How much should the company charge so that they could break even? So the first thing you need to do is find the expected claim amount. Without resorting to writing it as a formula, is it intuitive what the expected claim amount would be? Based on what I've argued with you for an expected value, you take this times this, plus this times this, plus this times this, and add it up. That gives you the expected claim amount. You scale each claim amount by the probability. It makes a lot of intuitive sense. So the number is pretty small because 80% of the time, no one claims anything. The problem comes when you try to claim things, and things happen so quickly. Now, was it a month ago with all the United Healthcare thing? Yeah. It's only when people start to claim amounts and they get denial of claim. They're very happy when you never claim anything, basically. Just leave them alone. Pay them the premium and then leave them alone. And that happens a lot of times. People don't. But when you try to claim, then you hear the claim amounts. So how much should the company charge as its premiums so that it can break even on cost? So this is one of the most basic actuarial calculations you can think of. So X is the random amount of claim people could make. And I hope you agree, the expected the expected claim amount is this. You scale each claim amount by the probability of it happening. And of course, arithmetic tells you this is 760. Which means what? On average, you should charge a premium of 760 if your intention is to break even. Of course, that's not the intention. So can you modify the question? If your intention is to make a net profit of 40 per customer, then you charge 800. Simple math. On average, people will claim 760. So if you charge everyone 800 on average, you would gain 40. Like that. This is just break even, which no one does. All right. Okay. Are we good with this example? Right. So very intuitive, right? Are we? I hope we're not bothered by this formula. This formula is just summation over all possible values of random variable scaled by a probability that value is the value taken by the random variable. Okay. Let's look at another one. An insurance policy provides the holder with a payment of 1,000 if a death occurs within 5 years. X is the random variable of the amount paid out from the insurance company to the policyholder. So suppose the probability of death within 5 years is estimated to be 15%. Find the probability distribution of X. What is X? So X measures how much gets paid out. So you have to always remember, is there a pretty high probability that they don't pay out anything? Yeah, because the probability of there being a death is pretty low. So your probability distribution should look like this. There is only a 15% chance that they pay out 1,000. And there's an 85% chance that they pay nothing. Because death does not happen. And so what is the most the policyholder should be willing to pay for this policy? How would you answer that question? You find the expected value, right? You should be only willing to pay no more than $150 logically, if you're going with expected values to guide your choice. The expected amount that people get paid is 150, so the policy, a fair amount, is 150. Of course, this is a highly simplified example, but it motivates expected values. All right? In the long run, in the population of people, the average amount that gets paid out is 150. So a reasonable premium is 150. Like that. Okay, another example. Okay, so an insurance company offers you $2,000 1-year coverage for a premium of $225. Now, a probability that the theft will occur is 0.1. What is your expected return from this policy? See? So you pay $225, don't forget. You paid $225 already for this policy. You will get $2,000 if there's a theft. All right? See if you can work this out before I show you the answer. Right? You've already put down 225. You bought the policy already. And notice I'm asking what is your expected return. So here's a hint. Right? Could you actually end up losing in a sense? Did you pay money for no reason? Yeah, that's how insurance works. That's why people don't like it. Right? You're out 225 if your thing did not get stolen. Okay. So see if you can work out what is your expected return. Write down the distribution, probability distribution of X. X is the return to you, right? Right? What do you get, and what's the likelihood of you getting that? So there are two ways to do this problem. You can do it the way I normally think about the problem is, well, there's a probability of 90% that my return is negative 225. So I paid the premium and it didn't get stolen, so it was a non-event. Of course, there's a 10% chance that it did get stolen. And then I get actually 1775 because I already paid 225 already. So my return is 4. Now, if you don't like this argument, you can also think of it this way. There is a 0.9 probability I get nothing, and a 10% probability I get 2,000. But don't forget to subtract 225 from everything because you paid that at the beginning. So that has affected in the end. So you either work it in while you do the problem, or you work it in at the end after you have accumulated it. So there's two ways of thinking about the problem. Either you think about it as I'm down this all the time, or here's what I get, but don't forget to subtract what you paid for because you're talking about your returns. Okay? Okay, one more example. Oh no, I think we are. Okay, so we are done with 76. 77 is one we're going to skip. 78, we're also going to skip. So we're going to go to 79. And when we skip a problem, just mark it on your examples, okay? So you don't think that it's something that's required. Okay, example 79. How do you find expected values of functions of the random variable? Okay, so I think there's some notes I want to go over. Yes, okay. So let's go over these notes. It's actually quite easy to know how to do the expected value of any function of the random variable. See, previously, I gave you the formula for plain old expected value. If it's just EX, expected value of X, then you just take the X terms and scale by the probability to compare the formula. So if it's GX that you want to find the expected value of, you just dump the function in here and scale by the probability. Is it intuitive? That should be the case. If it's just X that you're interested in, then this goes away. Then you just have X's scaled by probability. If it's GX, some function of the random variable, you put a function, that's it. So that function could be anything, okay? So let's go to an example, 79. Let X be the number of points on the side that comes up when rolling a fair die. Find the expected value of 2x squared plus 1. For some reason, I want to know what is the expected value of. See, X is the score on a fair die. But maybe I will pay you according to this formula. So you want to find out if you play this game where I pay you 2x squared plus $1, depending on the score X on your die. What's your expected score? You want to find the expected value of this. So how do you do this? So you find the expected value of 2x squared plus 1 pretty simply. You do what I just said. You cycle through the values that if you don't like I, you can say X, that's fine. Okay? You cycle through the values that the die can be, which is 1 to 6. But you insert the function that you want. That's it. Scale by the probability, which is, of course, 1/6 because it's a fair die with 6 sides. Did you see that? See, if you are trying to find just the expected score on your fair die, then it's just EX. Then it's just I times 1/6. Because it's 1, 2, 3, 4, 5, 6. And the answer is 3.5, by the way. When you toss a fair die, the expected score is 3.5. You get that by doing summation I times 1/6. Okay, my question to you is this. Does anyone in the class know what the answer is for this sum? And I put a note in my things to tell the class. You actually need to know some of these pretty basic sums like this. Does anyone know the formula for the summation of the squared whole numbers from 1 to n? Does anyone know it? Some classes I've had, there was one person that did know it off the top of their head. I'm quite impressed actually. I don't expect people to know. I just want to know, I'm curious to know, has anyone encountered this, actually memorized these things? Okay, what about the even simpler question first? Do you know what the sum of all the whole numbers from natural numbers from 1 to n is? Is there a simple formula for that? Yes.
It's like n/n+1 divided by 2.
Yeah, so good. N plus 1 over 2. So you can write that down. It's a useful sum to know. N plus 1 over 2. Okay, what about this one? I squared, where the sum of the squares of the integers. So I believe, don't quote me on this, but I've not used it for a while, but I think it's burned into my subconscious. N plus 1, 2n plus 1 over 6. I think so. It's n plus 1, 2n plus 1 over 6. These are useful things you need to, these have been established long ago. Okay? So you can just insert 6 into the formula to get the answer. Of course, you can do it the slow way and add, but n plus 1, 2n plus 1 over 6 is the summation of the squares from 1 to n. Now I'm going to ask you, does anyone know the formula for the cubes? You could sum up. Yes.
Like n squared times n+1 squared over 4.
Excellent. It is the n plus 1 over 2 thing squared. That's how I remember it. It is the original summation of I is n plus 1 over 2 entirely squared. That's what it is. And that's where it ends for me. I can't remember anymore. Okay. So these are just useful, especially in probability class, because sometimes you are called upon to find these things. I mean, now you can do a search online and AI will probably give you the answer immediately. But the point is, these are useful sums to know. All right. Okay. So I think according to yeah. Okay. So anyway, oh, I was right. n plus 1, 2n plus 1. Okay. So just make a note of that. It's a useful time-saving device to know things like that. And you know how to prove that it's true, right? You use induction. But this is not Math 280, so I won't be talking about that. Okay, so okay, let's look at another. Well, I think we are done with example 79. Yes, okay. I think it's time to go back to the slides. So just one more fact I want to point out. For constants a and b, the expected value, so if you have a very simple function, the expected value of constant times random variable plus constant is the constant comes out. So this can be thought of as an operator. So a comes out in b. Now, does it make intuitive sense? If I take a number and add it to everyone, shouldn't the expected value also be shifted by that? That makes sense. If I take a number and scale everyone by that amount, shouldn't the expected value be scaled by that? So this is very intuitive. But it's a very, very fundamental result that you can use. The expected values of ax plus b can be written this way. The number just comes out and the constant is removed from the expected variables. Everyone shifts out. How do you prove that for discrete random variable? Very easily. If it's infinite, then you might have to be a little bit careful about the summation and taking things out. But if it's a finite sum, it's a very easy proof. The function I want to find the expected value for is this. Scale it by the probability. You know how summation works. You can split the finite sum. And then constants come out of a sum. But what's this? This is EX again. And I want to ask you, what's this? What is the sum of all the probabilities over all possible values? This has to be, because this is a valid probability distribution. So the summation of all probabilities is 1. And so you have b times 1 and you have your result. Right? So I have in my notes that I'm going to discuss. I want to look at. Hold on. I want to look at example 79A. And okay, let me get example 79A first of all. Hmm. And if we can't finish this today, that's fine. But I think we have enough time. I want you to do this actually in your groups. Okay, this will be one of those ICPs where I want you to do this problem. So don't make your own problem, do this problem, right? So this will help you test your understanding of expected values with a slightly non-trivial kind of distribution. So an insurance policy pays 100 per day for up to 3 days of hospitalization, and then 50 per day for each day of hospitalization thereafter. The number of days of hospitalization is this variable. Okay. This is the variable that talks about how many days you are in hospital. Now, how likely are you to be in hospital for 1 day, 2, up to 5? You can't, according to this model, you can't be in hospital more than 5 days. Okay. Determine the expected payment for hospitalization at this point. So this is quite a good problem. I want you to, in your group, discuss. I'll give you a hint. Give me the payment function. Write down a random, define a random variable y. Right? Don't call it x. X is reserved for how many days you're in hospital. Call it y. Y is how much you get. We're not talking about premiums here, so don't worry about the complication. How much do I pay for the event? Just write how much does the insurance company pay you? It's clearly going to be a function of x. Now, do you understand the payment scheme? Okay, if you are in hospital for 1 day, how much do you get? If you're in hospital for 2 days, how much do you get? And so on. So try to work that out in your group, right? And we'll end with this one, all right? Set up a new variable called y for your what you get, right? What do you get? Y is a function of x.